If you have a single crystalline based memory resistor, you can control the switching behavior much better than amorphous material. However, in order to operate memory resistor, you really need to have defect inside memory resistor material. 2018, we kind of found a way to get around this dilemma by controllably injecting defect inside the single crystalline material, which can be done by growing silicon germanium materials on silicon wafer. If you do that, if there is lattice difference, crystalline structure difference between silicon and silicon germanium. So if you grow silicon germanium on silicon, you're supposed to have aligned, vertically aligned defect automatically, which is called dislocation. At that time, we found out that if you use this dislocation pipe, vertically aligned defect in single crystalline material, you can enhance the switching uniformity a lot. That way, we are able to demonstrate world's most uniform and controllable synapses using silicon germanium and silicon. At that time, we predict the accuracy of handwriting recognition by doing simulation using our device, which is almost up to the limit of software, which is 94 or 95%. After that, we've been working on this concept furthermore. So now we are able to fabricate the real artificial neural network hardware. Remote epitaxy has a very strong technical implication in many different fields. For example, if you grow gallium arsenide material on graphene and peel off by reusing the substrate, then you can keep replicating gallium arsenide material with a cheaper price. Then you can keep replicating high efficiency solar cell with much cheaper price. That is the motivation of working on photovoltaic devices using our remote epitaxy, which is growing materials on graphene on the wafer. So we have DARPA DOE project where we produce cheaper solar cell. And we have a DARPA project where we produce the flexible and cheaper photodetector by using different material, which is indium arsenide. We have different project where we use gallium nitride remote epitaxy, so then you can replicate ultra thin gallium nitride material with much cheaper price. So far, gallium nitride wafer itself cost like a couple of $1,000 to $10,000. Imagine if you can replicate this $10,000 material on and on by using our remote epitaxy technique. The impact could be very, very high. So we spun off the company out of this gallium nitride remote epitaxy concept, because the gallium arsenide material is very expensive, but the efficiency of gallium arsenide solar cell is one of the highest. Then it's obvious choice that you grow high efficiency solar cell with much cheaper price.